Hello everyone, welcome to my 10,000 questions mechanical series. And now it is episode 1. And question in this episode is restaurant diagram. Okay, let's get started. In the long year in the past, the human make the wood bridge, the hot cart, and wood house and wood ship. Yeah, in this time, all the things so really helpful for human, but when have storm or really complex weather and running in the long way is not suitable. For example, the wood ship when you running this ship in the far from in the ocean and we have some storm, and when that the wood is not good for not have a good strength to uh, uh, to stay with the really strong storm, and the wood house is the same and the wood bridge is the same. For example, you can see, imagine this brick, the wood brick for um, when the really high flock in this brick really easy destroyed by this flood, really dangerous. And you can see this is the horse cart. The horse cart is a long in year invented, but it's not suitable. It's not suitable for um, running long way from example from Hanoi to Hue or to Ho Chi Minh City is not suitable and it's so uncomfortable. Yeah, and now when we're using stress strain diagram in mechanical and in servo, we have concrete bridge, concrete bridge, and really huge metal ship, and really modern smart car, and really high tower, and it's really strong and really safety, modern, nice, and luxury, and it's really huge, so comfortable. All the things so strength in almost condition. For example, storm. This bridge can stay with the high storm, and for example, the ship and this tower so really big, and it can stand with the almost weather condition. Okay, we go to what is stress strain diagram. Okay, we have diagram of ductile material. Okay, today now I will explain step by step for you to understand all of the picture. Okay, this is the stress strain diagram, and this is the curve of when we have uh, experiment, yeah, experiment with the ductile material like steel, like aluminum. Okay, now we show you example. We have a stick, a steel stick like that, with the L is the length of this stick, yeah, and I will I will apply two forked in both sides of this stick. Okay. Okay. Are you ready? Are you sure? Okay. And its name is L1. This L is original length and L1 is when in this and when we have two forks in both sides of this stick. Yeah, we have L1, and here the length increase is delta L. Okay. I now will explain for you about stretch. Stretch is a formula. It is sigma. Yeah, and it divide fork divide area. This is the formula of stretch, and strength is epsilon equal delta L, yeah, divide L. Delta L, this is the length increase and divide for original length of this stick, okay, and stress strength. When I apply to fork both sides, we have a fork and the thickness of this steel stick is a area A. Okay, example diagram is 6 millimeter. Okay. Okay, we have um, two condition here, and you can I mark number 1 to number 2. This is um, the linear curve, yeah, and this into elastic region, yeah. Okay. When I apply the stretch A here, and we also have B strength. Okay, yeah, and you can see this is the Young modulus in number 1 to number 2. We have Young modulus fraction A is this strength and B is this strength. A divide B equal, yeah, equal with C and D. Sorry. Okay. A divide B, the fraction A divide B equal C divide D. The all fraction in this linear curve is equal, yeah, are equal. Okay, and it follow the Young modulus formula, the fraction stress divide strength. And I have note for you in elastic region from number 1 to number 3. Yeah, when you remove the fork of two of side of this stick, the length can come return with the original length, like spring. It's like spring when you stretch it, and when you remove the fork, spring is return original length. Okay. Okay, and number 2 to number 1 is the reason uh, allow maintain Young modulus fraction. Yeah. Okay, go to the, for example, I have a point in region 2 to 3. Yeah, here this is uh, this is H and G, for example. Okay, and here is not allow, it's not maintain Young modulus formulas. Yeah, but it's when it can return with original length, but it's not maintain the equal fraction like number 1 to number 2. Okay, the reason before the 3 point, the point number 3, the length of this stick can come back with original length. Yeah, like string. But straight in number 3 is not. For example, is R and N. Yeah. In this boy stay in flatic region. Yeah, we have a flatic region in here. For example, yeah, really high forks. It's increased fork into a side of this stick. So it is number L2. Okay, number L2. Okay, and in this situation, in this condition, the stick is not come back, not return with original length. When I remove the two side of fork into side, it just stay with the length, the length like this. Yeah, is not return with the original line or original length. Okay, this is flattish region. And okay, and go to go to 4 point. Point number 4, we have this is the largest stretch. Yeah, largest stretch marks. The maximum of stretch can apply in this stick and make it deformation. Okay, and after it, the stretch is discrete. Yeah, and the stick have nut in here, have a nut in here, and into number point number 5, fraction point, and is brought up in this point. Yeah. Okay, and number 2, the point number 2 is the proportional limit, and this is the maximum allowable stretch can maintain Young modulus. And number 3 is yield strength, and begin this strength we start plastic deformation, and before we in elastic region, elastic deformation. Okay, and number 4 is ultimate tensile strength. This is maximum of stress can apply in this stick, and it make deformation in this stick. And number 5 is fracture point. In this point, stick is broken up into part. Okay, So go to the next slide. I will show you compare with bowl and some material. And okay. Okay. Here we have a stress strain diagram, and in this diagram we have one, two, three, four. We have a four curve of four material. Okay, the number one, you can see brittle material like glass and um, ceramic, yeah, ceramic, and concrete, yeah, and ductile like steel, aluminum, copper, yeah, and strength softening like polymer and some plastic, yeah, and rubber, like you can, if you don't know rubber is mean in Vietnamese. So okay, I will continue. Okay, rubber in mechanical. In fact, rubber is really the material make the tire of bicycle, the tire of motorbike, tire of car. You can see every day. Yeah. Okay. Um, the first I can compare four of this material. The first is brittle. Yeah, you can see strand curve, and just a little bit uh, the curve, the circle, yeah, a part of circle curve here, yeah. I And this material is not the ductile material, little bit brittle, but that is not have plastic deformation. It just have elastic deformation, but you can see um, yeah, you can see it's really narrow, and the elastic deformation so narrow. The deformation of it is so really small, just a little bit. And okay, yeah, and the ductile, yeah, ductile here, yeah, the ductile, it have elastic deformation is bigger, the reason bigger than brittle, and it have elastic deformation here, like the uh, the previous diagram I show you, yeah. And this is strain soften is have elastic deformation, and also have a elastic, and rubber is have a so really small, yeah, really small, the elastic deformation, and hairy long, it's have long plastic deformation. Okay, and you can see brittle is really high for that, because it is straight. You need a lot of fork to push the two side of concrete, yeah, concrete, yeah, concrete here, concrete um, con- concrete box here, and you need really high fork to uh, stretch it, yeah, and it's really hard to deformation, really hard to increase the length, yeah, and brittle, yeah, brittle. This is brittle and ductile material. The ductile material unit lower the fault can make it uh, deformation, and the strength of is lower and lowest is rubber. It's easy to stretch, yeah. Now I have thing not for you. This is young modulus. It show up the material, how to hard material can get, yeah. This is uh, is a young modulus E, yeah. Okay, the size of young modulus E. For example, brittle, we have, yeah, have example for you. You can see the rubber have a really small angle here, and the brittle have really big angle here, and the curve, the brittle have the log angle is really hard, yeah, it's really hard, yeah, really hard, and have a small angle, it's really sharp, yeah, really sharp. Okay, and when engineer look at in this diagram, it can they can understand for material mm, and understanding the strength of it, yeah. Okay, go to application. When the engineer understanding and really recently look up the stress strain diagram in the school, and we have a knowledge about it, we can easily to choosing material. For example, the engineer to make the frame of a car, and they choosing material suitable for bending in this structure, and it can um, uh, it can stay with the compressive forks or tensile fork, for example, like this, and it can the engineer can design the safety uh, the safety structure, and can predicting the deformation of it of the structure by simulation, and avoiding failure. And finally, the engineer can have quality control of all of um, the manufacturing manufacturing condition, manufacturing process, yeah. And now stretch strain diagram is used in a lot, and um, apply in a lot of software, simulation software like ANSYS and SolidWorks, yeah. And in here you can draw the structure like this, and you have you have a condition here like fix here, fix here, and they have a fork here, and the software you can show you the bending deformation of this stick. Yeah, and when you apply the material here and the condition here and forks here, and it show you the dangerous reason, yeah, the dangerous deformation, and you avoid failure. Okay, this is really information of stress strain diagram application in mechanical or in servo. Okay, I hope you understand, and I hope you enjoy in this lesson. Okay, maybe it's the first time I make the video and show you this knowledge, and I hope in the next time I can improve my performance and help everyone is understanding all of the knowledge in mechanical. Okay, see you guys. It's next time. Thank you. Okay.